Hi, welcome back to the shop. Today we have a little bit of a tool making and tool modifying project. I have this DCMT boring bar here, which is a very cheap import boring bar from eBay. This costs like 10 euros or something like that. And it works just fine. I use it a lot because the way it orients the insert is very, very usable if you have to hog out a lot of material. But I'm doing regularly parts that require very deep bores, these plastic parts, and I have to bore them out 65 millimeters deep, that's about here. And while I drill out most of the material with a flat bottomed drill, I still have to do some boring, and having the boring bar with 10 millimeter shank diameter stick out that far tends to vibrate. Not as much that it is really noticeable in the finish, but it's bloody annoying when you run the machine. So my idea was to take this boring bar, chop it off, take a piece of 10 millimeter carbide, your regular solid tungsten carbide that's also used to make cutters, and silver brace a carbide shank onto it. And the idea behind that is module of elasticity of tungsten carbide is about 3 times higher than steel. It doesn't matter if the steel is hardened, soft, or it's stainless or tool steel. Steel always has the same module of elasticity, no matter the condition it is. That means with the same load applied to the cutting edge here, the deflection will be 3 times less. So that's what we're going to do. We'll cut it at an angle, and also chop the carbide off at an angle, and then do some silver brazing. So let's get this boring bar out there. As you can see, we will keep the shank about this length too. Let's remove the insert. We don't need that for our purposes here. So first step will be to cut it off at an angle and check if this is hardened. Wall put hardness tester, make sure this platter is clean. Make sure there are no high spots on here. And also make sure there is nothing strange up here. And we do a regular Rockwell C hardness check here. This boring bar has a flat on top and bottom milled onto it, so it's easy to check the hardness here. I'm going to preload it. And good. Okay, let's see what we get as a hardness. Yeah, this is 44 to 45 Rockwell C. That's still machinable. It's hard or tough, but not unmachinable with regular tools. You still can cut this with an hacksaw, for example. And that's also what we're going to do to lob it off. I don't want to cut 44 Rockwell C with my bandsaw because I have a brand new blade on it. So yes, it's tough. It's really some tough steel here. Lop the head off. Next we'll cut it at an angle and prepare the carbide blank. I'm holding the sawn off boring bar head in small grinding vise here at kind of 45 degree, and now I'm using this ground precision 45 degree angle piece to set the cutoff head in the vise to a proper angle. I'm doing that by pushing the angle piece into the corner between the vise and the boring bar head and checking the light gap. And when I'm satisfied with my result, I'm tightening it down and head over for the surface grinder. This is not a very rigid setup, but it will do fine for grinding. Using a 46 grit aluminum oxide wheel to remove all the material until the whole cross section of the boring bar is at 45 degrees. Cutting the carbide blank to length using a resin bound diamond wheel on the tool and cutter grinder by spinning the carbide rod into the grinding wheel. And then with the same setup, just tilted at 45 degrees, I'm using the same cutoff wheel to cut the end of the carbide rod to 45 degrees. And of course, the cutoff that I removed landed in the dust extraction. I have both parts in V-blocks, and they're riding against the back rail on this piece of precision ground flat stock. And by pushing the two V-blocks against each other and having the carbide shank loose in the V-block, the two angle cuts align to each other quite nicely. Using a diamond burr to scuff off both surfaces that get silver soldered. Here you can see the coolant channels that this carbide blank has in it. This is a twist drill blank. The coolant channels in it are twisted. Adding the high temperature flux to both sides. And this is the silver solder I'm using. It's Fontaine A340, which is a 40% silver content solder. Using a small rosebud torch on my oxy fuel setup. 10mm round stock will take some significant heat to let the solder flow freely. Also, those V-blocks are acting quite a bit as a heat sink, but the rosebud takes care of this very easily. And yes, I'm kinda roasting the left-handed V-block, but it is what it is. Just getting everything up to temperature. For silver soldering, it kinda needs to be dull red glowing to make the silver solder flow. Also, the condition of the flux is a good indicator. Once the flux melts and gets completely crystal clear like glass, you're good to go. So this is the right moment now. Now the silver solder will melt on the joint, as you can see, and it wicks into the joint very nicely. Then it's important to keep up the heat for a few seconds to give the solder some time to wet over the whole surface. Also, it's a good idea to move the flame around a little bit. Would be neat to go in with the flame from the back side. But a quick inspection told me that the silver solder did not come out on the underside yet, so added some more heat. Now I'm going to the back side, helping it a little bit flow and calling it a day. Silver soldering is also one of those tasks you need to know when to stop, and that was the right moment here. So I bead blasted the silver solder joint to get the remaining flux off, and as you can see, the silver solder flowed all the way nicely around the joint. I put primarily silver solder up here, and it wicked down into the joint all the way around, and as you can see, there is no weird spot here. Next will be to indicate this flat here that used to be on the boring bar. Indicate it, get it aligned in a vise, and grind the same flat on here. Then flip the boring bar around and surface grind the same flat onto the bottom, so the orientation of the insert in relation to the world is the same as before. Well, let's go. We'll just put it in a vise, go on the surface plate and traverse with an indicator on here and spin the boring bar until we get a parallel. So we're at the surface plate. I have the boring bar with a parallel in my drill press vise, and I'm sweeping this little bit of flat here with the indicator and also moving the boring bar at the same time to get it parallel. Okay, that was too much. Yeah, there's probably an easier way to get this done, but in the end, it's a very fast way what I'm doing here because the setup is minimal. So it's high up here. So we started 30 here, 32. Depending on precise, this flat was milled previously. We zero out here, and over here we got slight minus. Maybe 50 microns minus. So that's good enough for this. This orientation of this flat just determines how much the insert is tilted to give additional clearance if you go into a small bore with this boring bar. So it's not crazy critical. Clamped it. Now we go to the surface grinder and put a new flat on here. And then we flip it around onto the parallel and do the same on the underside. Okay, ground the flats on both sides of the boring bar. Now I just need to, or want to, clean up the silver solder joint a little bit because I have some overspill of silver solder on some spaces. So I'm using not my best file because we're running it on steel and carbide here. So that's not good for the file. Also, I was called out for my filing technique because I sometimes drag my file. Sometimes I drag my file, sometimes I will take off weight when I retract the file, and sometimes I will lift the file. It depends entirely on what I'm doing with the file. And obviously, or for some reason, if you have this in the mind of some people, the wrong filing technique, they get really worked up on you. And then I have to block you. So this is really now death to a file. This is killing the file. It's a little bit hard to file with the camera in the way, by the way. Also using a small Cratex wheel to do some additional work here. Okay, thank you. Final step, some Scotch-Brite. And here we go. Solid carbide shanked boring bar. Good to go. So this is the actual cut that I made this boring bar for on this part. And it's dead silent now. Even if this is a fairly light cut, before with the steel shanked boring bar, this exact same cut was screaming like mad. It was vibrating, resonating, and it was really, really loud and annoying. Didn't affect the surface finish significantly, but you didn't want to take the cut because it was just loud. So success on this side, I would say. I have a little experiment prepared here. I have my grinding vise in my bench vise, using the grinding vise because I aligned it so the jaw is horizontal, and when I put our test specimen in here, I'm loading it against the jaws, and with the bench vise I would try to rotate it out of the jaws, so this is more safe in this case. Mounted my indicator stand to the back side of the grinding vise, and I have a 1 micron reading Mitutoyo Hikator in here. And what we want to do is here, we want to compare the bending under load of 3 different materials. I have solid carbide, which is the material that we used for the boring bar. We have a piece of 14112, which is, I think, 440B stainless, which is a hardenable stainless steel, but it's in soft condition here. And I have 17225 QT, means quench and tempered. This is your basic 4140 chromoly in a commercial heat treat. Since I don't have a calibrated weight, I'm just gonna use a bottle of water, 0.75 liters, and the bottle weighs a little bit too, so we should be pretty close to 1 kilogram. Of course I don't have a scale that accurate, because why would I? So let's do some science here. We put this in the vise. The vise has a V-block, so this makes aligning the stock very easy. The distance from the bending point towards the indicator is 85 millimeters. And I will put the load at 90 out here. I engineered this nice wire loop so I can hang it off the carbide. This is carbide rod, and we can hang the weight here. So let's zero out the indicator. There we go. That's repeatable. That's always going back to 0. And now we weigh it with our 1 water bottle standard. So here we go. And that's exactly 13 microns. Half a thou for the imperial guys. 13 microns. We'll put that here on the notes. For carbide, goes back to 0, kinda, almost. Keep in mind that measuring 1 micron increments is an incredible small dimension, and every little bit will affect this. So now we go for the 14112 stainless steel. This is some nice precision ground round stock. Zero out. We need to re-zero the indicator with each bar, because these bars are obviously not round and not perfectly the same diameter. So yeah, we got our repeatable 0 here for the stainless steel. Mark our 90 millimeters. That's all, of course, very scientific and very, very accurate what we're doing here. So don't even think about taking this with a grain of salt. So we weigh this down and we go down to 32 microns. 32 microns compared to the 13 micron of the carbide. We'll put that number here for the stainless steel. Go back to 0. and get rid of the spar. And now we have the 17225 QT, the 4140 chromoly. Lock it on the vise here. Mark our 90 millimeters again. So I'm using 90 instead of 100 because why not? There we go. That's reasonably repeatable. Now we drop our bottle on here on the chromoly steel, which is hardened. It's hardened and tempered. So this will go the same way. This is 35 micron even. So considering tolerances and our setup here and different loading and my high precision water bottle with the high precision wire coat here, wire coat hanger, that's reasonably accurate enough to be pretty much the same than 32 micron. We're relatively close to 3 times more deflection under load than with the carbide, which is in my mind significant. And industry tells us that it's significant because that's the reason why carbide boring bars exist. Let's see if we can get this boring bar in here with 90 millimeters extension, but I think this might be a little bit on the short side to get it to 95. Yeah, we'll see. Need to drop the indicator a little bit. Get back to 0. Check our 0. Note that I put it in the vise vertically with the flat not affecting the stiffness as much as it would be laying down, so we can compare it more or less to the other round stock. Now we check our 90 millimeters, and that's right behind the insert, right here. So here we go. So we get 14 microns of deflection. I wish I tested the boring bar before I cut it apart while it still had its steel shank, but I completely forgot that. But you get the idea. This is significantly stiffer than the steel bar that we used previously for our experimentation here. So, considering all things, and also considering what a carbide shanked boring bar from a tooling manufacturer costs, this was in my mind worth the effort. It wasn't too much work. Lobbing off the carbide, cutting off the boring bar. Boring bar was relatively cheap. Silver brazing, cleanup done. Considering all things, this was a fun little project, and it helped quiet down these plastic parts that are turning a good amount, and my ears are thanking me. So I hope you enjoyed this little tool making project. Thank you all for watching, and I'll be back.